Hello, guys. Welcome back to Engineers Academy. Do hit the subscribe button if you are here for the first time. Now we are going to solve this problem from Vector Mechanics for Engineers by Baer and Johnston. And the problem says that a small boat hangs from two davits, one of which is shown in figure. It is known that the moment about the z-axis of the resultant force or A exerted on the davit at A must not exceed 279 pound-feet in absolute value. Determine the largest allowable tension in ABAD wire when x is equal to 6 feet. So if this x is equal to 6 feet, we need to find the maximum tension in this wire so that we must have the moment about the z-axis equal to 279 pound-feet. So we are given that the moment about the z-axis is 279 pound-feet. We have already solved this problem in problem 322. I will give the link in the description. We have already discussed about how to find the resultant of the tension and how to find the moment of that resultant. But now this is something different. We have to understand it differently from that particular problem. You guys can go and compare both the problems, and that will increase your knowledge. Must watch that 322 problem. Now in this problem, we are given that the moment of the tension in this whole wire about the z-axis is 279 pound-feet, and it must not exceed. So we have to find the tension in this rope, and that tension must be the maximum allowable tension according to this particular moment about the z-axis. So now for that, I have to cut these ropes in order to consider the forces at point A, since we want to find the moment of the resultant at A about the z-axis. So for that, I have to cut these three ropes here. You guys can see, and here. So now let's say that we have here we have two forces. Let's say these two forces are tension AB, and let's say we are considering them as a vector. So two tension vectors in the downward direction and one tension in this direction. So we can say that we have TAD. Now we have already discussed this, that the resultant at point A will be equal to the vector sum of, this will be 2 times TAB. So 2 times TAB plus TAD. So we can say that the moment about the z-axis will be equal to the cross product of the moment arm. So let's say that the moment arm will be from the vector from C to A, cross product with the resultant of A. So this is the vector method, right? So now you guys can see that we have to find, for this vector method, we have to find this resultant first, and then we have to apply this cross product. So let's do both the problems. One method is the scalar method. In the scalar method is the easiest method, and we will discuss it later. So first of all, let's find the resultant at A. So we can say that the resultant at A will be equal to, so first of all, let me find TAB. So TAB. So the magnitude in the whole rope of the tension remains the same. So let's say that the magnitude is T. So TAB will be equal to T times, this TAB vector will be equal to the magnitude T times the unit vector from A to B. And the unit vector from A to B is, you guys can see that this is the positive direction, so the unit vector is in the negative J. So it is in the negative y direction. So we can say that TAB will be equal to T times negative J. So if this is TAB, so TAB is minus TJ. So 2 TAB will be 2 times of this. So let's write that 2 TAB vector will be equal to minus 2 TJ. Similarly, let's find TAD. So TAD vector will be equal to T magnitude. The magnitude remains the same in the whole wire ABAD. and this will be equal to the unit vector from A to D. Or we can say that the unit vector from A to D. So this will be T, and the unit vector from A to D will be the position vector from A to D divided by the magnitude of that position vector. So this will be equal to T. Now we can find the position vector from A to D if we start from A and traveling along the x, y, and z axis in any sequence. So let's say from A we need to move 3 feet in the negative z. This is the positive z. We are moving in the opposite direction. So 3 feet in the negative z means 3 feet in the negative k. So I will reach somewhere here, and then from here I need to travel 7.75 feet in the negative y. So that is in the negative j. So we will write minus 7.75 in the negative j. So we will reach the origin, and from the origin we need to travel this 6 feet in the positive x. So 6 feet in the positive x means in the positive I. And now the magnitude will be 6 square plus 7.75 square plus 3 square under the square root, and this is equal to, this magnitude is equal to 10.25. So this is equal to 10.25. So let's write this as 10.25. This will be in feet, and similarly these are in feet as well. So the unit vector is unitless. Feet divided by feet is no units. So now you guys can see that TAD vector will be equal to this T multiplied by this, or we can say T into 6 divided by 10.25 I, 6T divided by 10.25. Similarly, we can write 7.75 T divided by 10.25 J minus 3T divided by 10.25 K. 0.585 I, and with T 0.585 Ti and minus 7.75 0.756 J, and 3 divided by 10.25 gives us minus 0.293 K. So this is the tension from A to D. Is the vector representation of that tension, which has the same magnitude of T. So now if you find the resultant, we can say that the resultant at A vector will be equal to 2 times TAB plus TAD. Now we know 2 times TAB vector, which is minus 2TJ. We can say minus 2TJ plus this vector. So we will write this as it is. So this is that vector. Now we can add this with this, and remember that here we have the t's as well, right? So this is, here we have the t, remember. So this is the t and this is the t. Now we can say that we can simplify this. So this resultant will be 0.585 Ti, and we can add this minus 2 plus this. So this will become minus 2.756 Tj and minus 0.293 Tk. So this is the resultant at that point A due to the tension in this wire. So once we find this RA, we know that the overall moment of this resultant will be the unit vector from C to A, the position vector from C to A, cross product with the resultant at A. So sorry, here I have written this moment about Z. This is not the moment about Z. This cross product will give us the moment about that point C, which will have moment about the x, y, and z axis respectively. So this equation will give us the overall moment about that point C. So we can say that this will be the moment about point C. So let's write this as moment about point C. So we will have moment about point C equals to this. And once we find the moment about point C, the z component to find the T max, that the maximum tension in that cable, we have to equate the Z component of that moment about point C equals to this, because we are given the moment about the Z axis. So we can say that the moment about point C in the determinant form will be I, J, and K, and then the position vector from C to A. So we have to find the component of the position vector from C to A. So as you guys can see that from C, we need to travel 7.75 in the positive Y, that is in the positive J. So the J component will be 7.75 feet. And similarly, from there, we need to travel 3 feet in the positive Z, that is in the positive K. So 3 feet in the positive K. And there is no need to travel in the X. So the I component of the position vector from C to A is equal to 0. And similarly, now we know that this is the resultant at A. So this will be 0.585 minus 2.756 and minus 0.293. And we can take the T outside because the T is common in this row, so we can take T common from this particular row. So this will give us the moment about that point C. So let's find this. This will be moment about point C vector. This will be equal to, so for I, we have to hide this row and this column, so this minus this. So we can say 7.75 into minus 0.293 minus 3 into minus 2.756, and this will be I. Similarly, for J, we have to hide this row and this column, so 0 into this minus this. So this will become minus, and this, and with J, we always have the minus sign. So let me write this is minus for J, that will be minus 0 into minus 0.293 is 0, and then minus 3 into 0.585 J. So 1 minus is for this and 1 minus is for the negative 3. So this into this. And similarly for K, we have to hide this row, this column, 0 into this minus this. So we will write plus and 0 into that, and 7.75. Let me write this as minus 7.75 into 0.585 K. The I component is 7.75 into minus 0.293 minus 3 into minus 2.756. So this is 5.99. So this is approximately 6 pound-feet I, and multiply by that T outside. And similarly, the J component is minus into minus 3 is plus 3. 3 multiplied by 0.585. So this is plus 1.755 J. And now the K term is 7.75 into 0.585. So this is, we can say this is minus 4.534 K. So now we can say that the moment about point C vector is 6Ti plus 1.755 Tj minus 4.534 Tk. Now the moment about C, the component of the moment about C along the z-axis is equal to minus 4.534 Tk. What does this mean? Is the moment about the z-axis, so the thumb must point out in the negative z direction. So you guys can see that the moment about the z-axis is in this direction. So if we curl our right hand fingers in this direction, in this direction, the thumb must be in the negative z direction. So if you look from this direction, so the moment about the component of the moment at C about the z-axis is in the clockwise direction, and this is the direction. So and the magnitude will be the the magnitude of the moment at C about the z-axis will be equal to, or we can say that mcz magnitude, that is equal to 4.534 t, and which the problem says that this must not exceed 279 pound-feet. So that will give us that T max in that row. So now we can say that T max is equal to 279 pound-feet. Remember that this 4.534, this is in feet. So we can say that this is 4.534 feet. And now we can say that 279 divided by 4.534, this is equal to T max is approximately equal to 61.54 feet. So in order to have the Z component of the moment at C must not exceed 279 pound-feet, that tension in the rope must be 61.54 feet. Now let's use the scalar approach, the scalar method. Now the scalar method is very easy. Now you guys can see that once we have determined the vector from A to D, once we have determined this, we can easily find, if we know the scalar method. So the vector, the tension from A to D vector is like this from A to D, and it has three components. This is the x component of that TAD, this is the y component, and this is z component. Now you guys can see that the x component is in the positive I, the y component is in the negative j, and the z component is in the negative k. So let me represent those components. So the x component is in the positive x. So we can say like this, and I can put it here because we want to find the moment at A. So this red vector represents TAD x component. Similarly, we have the y component. So the y component is in the negative, the z component is in the negative z, and the y component is in the negative y. So this one is TAD y, this one is TAD z. Now we are given the moment about the z-axis. We are given the moment about the z-axis. Now look for these three components. Now you guys can see that this 2TAB, they are intersecting with the z-axis. Or in other words, we can say that the moment of this 2TAB vector from that z-axis is 0. So this means that these two tensions, they are not going to produce the moment about the z-axis. So they are not able to produce the moment about the z-axis, since the momentum of these two vectors from that z-axis is 0. So they are not going to produce the moment about the z-axis. Now this y component of TAD is also passing through that z-axis. It's intersecting with the z-axis. It's not going to produce the moment about the z-axis. So it's not going to produce the moment about the z-axis. Similarly, this z component is parallel to the z-axis. It can only accelerate this point A, or it can only move this point A along the z-axis. It cannot produce the moment about the z-axis, this particular component. So the only component of TAD in the x is going to produce the moment about the z-axis, and this TAD is producing that clockwise moment that we have just discussed. So TADX is producing the moment about the z-axis in the clockwise direction, and that moment must have the magnitude of this 279 pound-feet. Now we know that TADX is producing the moment. So now TADX is having a magnitude of 0.585 t. So we can say that let me write that TADX is producing the moment about the z-axis. Now the moment arm of this TAD x from the z-axis will be the perpendicular distance, this perpendicular distance, and this perpendicular distance of TADX from that z-axis is 7.75 feet. So we can say that TADX into 7.75 we can say that 7.75 into TADX will be equal to the magnitude of the moment about the z-axis, which is given, which is 279 pound-feet. And remember that this 7.75, this is in feet as well. And we know TADX magnitude. TADX magnitude is 0.585 T. So we can write this equation is 7.75 into 0.585 T equals to 279 pound-feet. And now if we equate this to 279, this is that T max that we want to find. So T max is equal to 279 divided by 7.75, 0.585. Now you guys compare this from where we got this 4.534. We got this from 7.75 into 0.585. You guys can see. And here we have that same number, 7.75 into 0.585. This will give us that same answer. So T max is 279 divided by 7.75 multiplied by 0.585. This is equal to 61.54. So T max is 61.54 pounds. So I hope all this discussion will help you in your learning. Let me know in the comments if this helps. Do subscribe Engineers Academy for the solution of such more problems from Vector Mechanics for Engineers by Bear and Johnston.